Well, see, enthalpy of combustion or standard enthalpy of combustion, right? Both have same meaning here, or standard standard enthalpy of combustion, right? Combustion. So the proper symbol for this is delta H, C for combustion, not, right? So see, like enthalpy of formation, we can define this enthalpy of combustion also. Enthalpy of combustion is basically it is defined for organic compounds first. Initially, that compounds having carbon, hydrogen, oxygen, they are converted into carbon dioxide means if you make the combustion of any compound, organic compound particularly having carbon, right? So this carbon will convert into carbon dioxide, and hydrogen is convert into what? Water. So if in any reaction carbon is converted into carbon dioxide, hydrogen is converted into water, and if oxygen has organic compound or compound having oxygen, then there is no product with respect to oxygen. Nitrogen, if there is present in the organic compound or any inorganic compound, then this is also non-combustible element under normal condition, right? So these are the general definitions. Already we have discussed about this in the idiometry, right? So basically this enthalpy of combustion is very much limited for the compounds having carbon, hydrogen and oxygen, basically carbon hydrogen or carbon hydrogen and oxygen. But with respect to oxygen there is no product, with respect to nitrogen there is no product under normal condition. So here I am putting one condition: under normal condition, under normal conditions, right? If you do electric spark, if you put electric spark there, or if you lightning is there, then nitrogen may combines with oxygen. So first you should understand what is this combustion reaction. So combustion reaction is basically complete oxidation reaction of compound with oxygen, so that carbon is converted into carbon dioxide. If carbon is not converted into carbon dioxide, then it is not combustion reaction. Remember, so carbon is converted into carbon dioxide, hydrogen is converted into water. If in any reaction of the given compound, then it is called what? Combustion reaction. Okay. So we can define this. The net heat change, because definition is very important. The net heat change in the combustion of combustion. Combustion means complete oxidation of 1 mole of given substance under standard conditions. standard conditions. Right? So all of you are knowing standard condition. So what are the key terms in this definition? Net heat change means in some step maybe absorption of heat takes place in at some step, or in some step release of heat may takes place, but you have to consider net heat change in the combustion, complete oxidation of 1 mole. This is very important. 1 mole of given substance under standard condition, and all of you are knowing what is the standard condition: 1 bar pressure and constant temperature. And if temperature is not mentioned, then it is 298.15 Kelvin, right? So this definition, basically the most important part is here 1 mole. If your compound is 2 mole or 3 mole, then that is not enthalpy of or standard enthalpy of combustion. Then it becomes what enthalpy of the reaction. Okay. And one very important point here I would like to mention that this enthalpy of combustion is always exothermic. So enthalpy of combustion is exothermic, right? Means delta H combustion, it is negative, right? So whatsoever the reaction, for all the reactions enthalpy of combustion is always exothermic. Clear to everybody? Okay. So see how to design this reaction of this combustion. Suppose that any general hydrocarbon is given CXHY. Suppose that this is gaseous at 1 bar pressure and 298.15 Kelvin. So you have to put gaseous, make the reaction with oxygen, and you will get X moles of CO2 gas plus Y by 2 moles of H2O liquid at 298.15 Kelvin and 1 bar pressure. So this is the standard condition. Here you cannot take more than 1 mole, so you have to balance this equation accordingly. So here X plus Y by 4, right? So whatsoever heat energy is changing under this situation, that is called enthalpy of combustion. Enthalpy of combustion for CXHY, right? And this is minus A kilojoules per mole. So here the enthalpy of combustion of this CXHY is A kilojoules per mole. And if it is asked that heat of combustion, so the heat of combustion means how much heat energy is released from the system. So sometime in tables you may get this value positive, but every time you have to understood like this, that if we are talking about the enthalpy delta H combustion, so this is minus A kilojoules per mole. But if it is asked that okay, find the amount of heat energy released from the system, then you have don't write minus A, so you have to write only A, because you have already written this negative sign in the your language, that the amount of heat energy released, because this negative sign indicates the amount of energy released, right? Don't associate this negative sign with the magnitude. So suppose that for any reaction Suppose that for any reaction, if delta H combustion for any reaction, suppose that X gives Y, suppose that for this it is minus 20 kilojoules per mole, and delta H combustions for another reaction, this is reaction 1, and for another reaction, A gives B, this is reaction 2, and this time this is minus 40 kilojoules per mole. So if it is asked that for which reaction enthalpy of combustion is more, so if it is asked that for which reaction the enthalpy of combustion is more, right? Suppose that the question is asked. So what is answer for this? The answer is for reaction 2, right? This 40 kilojoules. See, negative sign indicates that this amount of energy is going out. How much energy is going out is 20 here and here 40. So don't consider this negative sign with the magnitude here in thermodynamics. Clear? Everybody? It is clear? So for reaction 2, the enthalpy of combustion is more, right? So the enthalpy of combustion for reaction 2 is more than the enthalpy of combustion for reaction 1. Clear to everybody? So every time whenever you are comparing the enthalpy, don't consider this negative sign, right? You should consider only magnitude. Okay, see, this sign is determine the direction of flow of energy. This will determine the direction of flow of energy. So don't associate this with the magnitude. So in this way, you can define the enthalpy of combustion, right? Good. Well, see one example. Uh, delta H not combustion for benzene C6H6. It is given minus 3267 kilojoules per mole. So, and find the formation, means combustion is given here and formation they have asked. Okay, so how to proceed such questions? First, you have to design the equation for which the enthalpy is asked, right? What you have to do? Because in this question there is no equation, and you are not able to find out the answer of this question until or unless you are not equipped with the designing of the equation. If someone fails to design this equation, he or she cannot solve this question. So first start with the derive the equation, design the equation, write the equation for which the enthalpy is asked. So formation. So all of you are knowing that formation is always shown from the most stable elements, and carbon and hydrogen are there. So carbon most stable allotrope is graphite. So you have to take carbon graphite, already solid, no need to write this solid, and hydrogen, the most stable form of hydrogen is H2 gas, and this will give you the C6H6 liquid, C6H6 liquid at 298.15 Kelvin and 1 bar pressure. So C6H6, so here you have to multiply this with 6, and 6 hydrogen is required. This is 3. Don't put here 2 or 3 or 4. You always balance this equation, thermochemical equation, by considering, by taking 1 mole here only. So whatsoever the, energy changing in this, that is called enthalpy of formation for C6H6 liquid. Okay, this you have to calculate. Now come to the data which are given in this equation. So three data are given in this equation. One is combustion for this, one is combustion for this, and sorry, formation for this, and other is formation for this. Okay, so now you have to design each and every equation. So this is the desired equation. Now on the basis of three different equations, you have to manipulate algebraically those equations to get this equation, right? This is the simple task. So if you follow the steps explained to you, definitely there is no problem to solve such type of questions. Now combustion of benzene. Combustion of benzene C6H6 liquid. For all the reaction, this is the standard state, right? So don't write every time. C6H6 liquid plus O2 gas gives you CO2 gas plus H2O liquid, right? Keeping here 1 mole, because this is a combustion and defined 1 mole for only for the given species, so you have to balance this equation. So 6 CO2, 3 H2O, 6 to the 12, and 3 15. So here 15 by 2, right? And the combustion data is given here. For this reaction, the enthalpy change is given minus 3267 kilojoules per mole, right? Very good. Now design the equation for the formation of carbon dioxide. So this is the combustion of benzene. Combustion of benzene, right? Now let the, this is the equation 1. Now come to the next equation, that is the formation of carbon dioxide. So formation of carbon dioxide, formation of carbon dioxide, which is gaseous at the given condition. So all of you are knowing that for the formation, you have to take the most stable form of carbon, so carbon graphite plus O2 gas, and I think equation is balanced because here 1 mole should be there. Delta H formation, it is given 393.5 minus 393 minus 393.5 kilojoules per mole. Okay, and this is equation 2. Okay, now next is the formation of water. Formation of water, H2O liquids. So H2O liquid, most stable form of hydrogen is H2 gas, and of oxygen is O2 gas. Here keep 1 mole, so you have to balance like this, and this is equal to minus 285.83 minus 285.83 kilojoules per mole. So this is the formation equation for the formation of water. But very interestingly, if you see here, this is the same reaction for the combustion of hydrogen. And if the reaction is same, everything is same, then enthalpy is also same. So sometime examiner may confuse you. So remember, this is very important point. So here, this is the same reaction you will design for the combustion of hydrogen. So this is equal to, you can write delta H naught combustion of hydrogen. Yes. Very interesting. Very interesting point. Because if examiner asked, okay, design the equation for the combustion of hydrogen, so you will design the same reaction for the combustion. So if the reaction is same, coefficients, all things are same, then the enthalpy is also same. Now see here also, this is the combustion of carbon, formation of carbon dioxide. So this is equal to the combustion of carbon. So this is also equal to the combustion of carbon graphite. Carbon graphite. So if sometimes it is asked, okay, what is the reaction for the combustion of carbon graphite? The same reaction we will write and same enthalpy will change there. Clear to everybody? Now see, this is equation 3. Now you have 3 equations. This is equation 1, this is equation 2, and this is equation 3. And by using these 3 equations, you have to derive this equation. So in this equation, the coefficient of this carbon graphite is 6. So where you are getting carbon graphite, you are getting in the equation 2 graphite. So if you multiply this equation with 6, if you multiply this equation with 6, this with 6, right? So equation 2 multiplied by 6, right? So you are multiplying this 6 here, 6 here, 6 here, and 6 here also. You require 3 hydrogen. So this equation must be multiplied with 3. So you get here 3. So equation 3 is multiplied with 3, right? And carbon and hydrogen you want in the left hand side, okay? And this benzene you want right hand side, you want this benzene on the right hand side. So what you can do, that equation 2 multiplied by 3 plus equation 3 multiplied by 3, no, equation 2 multiplied by 6, equation 3 multiplied by 3 minus equation 1. So we will get the desired equation, right? So if you multiply equation 2 with 6, equation 3 with 3, and subtract equation 1 from these two, right? Addition of these two, so you will get the desired equation, right? So do all these things. So 6 carbon graphite, 6 carbon graphite plus 6O2 6O2 gas and 3H2 gas plus 3 by 2 O2 gas. So this is the left hand side, and minus this equation 1, C6H6 liquid minus liquid minus 15 by 2 O2 gas will give you 6 CO2 gas plus 3 H2O liquid minus 6 CO2 minus 3H2O. So left hand side I have added and subtracted, and right hand side added and subtracted. Now rearrange the terms. 3H2O liquid cancel, right? 6CO2 cancel, and 6 O2 plus 3 by 2 O2, 15 by 2 O2, 15 by 2 O2, 3 by 2 O2, 6 O2 cancel, right? So whatsoever left you can write. The left is 6C graphite plus 3H2 gas. This will give you C6H6 liquid. Now you can take in the right hand side. So all algebraic rules you can obey here. So this is the formation of C6H6. This is equal to, now do the same thing with the data, minus 393.5 minus 393.5 into 6 minus 285.83 into 3, 283, 285.83 into 3, and this plus this minus this. So minus this will plus 3267 minus 3267, right? So if you solve this, so you will get what? 48.51 kilojoules per mole. So this is the answer, right? So in this way you can calculate the enthalpy of formation of benzene, and which is a positive value here, and this is the exact value in fact for this formation of benzene, right? So this is the way how to solve such type of problems. Okay, clear to everybody? Good. Now see, this is very important note here I have mentioned for you, and everybody should write it very carefully. This is very important note. If all thermochemical data to be used in predicting an enthalpy of reaction for a desired equation, right, are enthalpies of combustion, means if in any question whatsoever data is given to you for the calculation of enthalpy of any reaction, all data are enthalpy of combustion, then the Hess law of Hess can be expressed as this. See, negative sign we are supposed to use here to express this equation. Nu I, the stoichiometric coefficient in the desired equation, and it is positive for products and it is negative for reactants. So try to understand this formula by taking a general equation. So everybody first you have to write this formula, then I'm giving you the idea how to apply on the equation. Suppose that your equation is AA plus BB gives CC plus D capital D. So the enthalpy of this reaction, standard enthalpy of this reaction can be explained in this form. You have to put negative sign first, this, and C times C, this is the coefficient, positive for product, so I am taking first product, C, delta H combustion for this C plus this D, because this is also positive, delta H naught combustion for D. Now this bracket close, right? Put negative sign here as usual way, and after that negative for reactant. So A, you have to take here minus A, delta H naught combustion for A minus B, delta H naught combustion for B, right? So if you compare, here in this formula, see how we have used this formula for the formation. We are using like this. This is C and D product. This is positive, and reactant, this is negative. But if we see here in this equation, then this time product is negative and reactant is positive. So this is the difference. So every time students are complaining, sir, my this sign is not matching, magnitude is matching, but sign is not matching. So this is the reason. Because this for combustion, if combustion data, see all the data I have taken here, combustion, then only you can do like this. And this is, I have clearly mentioned here, that if all thermochemical data, if all, not one or two, if all thermochemical data to be used in predicting an enthalpy of reaction for a desired equation are the enthalpies of combustion, means if all the data which are given to you all are combustion, then you have to use this equation. One negative sign is used here, right? So in the this is a very important point. So if you are not consider this, definitely your answer will not be matching your correct answer. Okay. Now see, I have one question for this. Suppose that delta H of this reaction is asked, and all the combustion data are given, right? All the combustion data are given. So see how to find the answer of this question. Delta H of this reaction is equal to minus combustion delta H, 1 mole is there, 1 mole into delta H combustion. I don't no need to write. delta H not combustion of C7H16, and the coefficient is positive, and plus delta H not combustion for hydrogen, right, bracket close, minus delta H of combustion of C6H14, and minus of delta H not combustion for CH4, right? All the data is given to you. Now you can very easily find the answer. Minus C7 minus 4811 minus 4811.2 kilojoules per mole, plus hydrogen is minus 286.1, don't write kilojoules per mole, minus delta H combustion of this, so minus 41413, 4141.3, minus methane is 882, right? So this is equal to minus 4811.2 minus 286.1 minus 4141.3 plus 882, right? So this is uh, minus 5097 minus 5097.3 minus, this is 5023.3. So this is equal to 5097.3 minus 5023.3. So this is equal to 74 kilojoules per mole. So this is the answer, right? So if you are doing in this manner, then your answer is always what? Correct. Otherwise magnitude will match, but sign will not match, right? Remember. So if combustion data are given, and it is asked that find the delta H of any reaction, then you have to use this concept, this equation, this concept for the evaluation of or calculation of delta H of the reaction, right? Hopefully all of you are clear and remember this, right?